Okay, so this is a little supplementary explanation on normal force on an inclined plane. An inclined plane could be anything in which an object is sliding or could be sliding down has some sort of angle. In this case, we'll call the angle theta for the general case. And really the question is, one you probably haven't had before, but the question is, why does the normal force on an inclined plane equal mg cos theta? And so we're going to go through the free body diagram on the inclined plane, and it's something I do expect you to know and to be able to show me on any questions you have on a test or exam related to inclined planes. And it would be sort of a communication mark that you understand or that you can demonstrate, why the normal force is what it is. Okay? And one key part of figuring this out or understanding it is looking at the x and y directions slightly different on an incline. Normally we think of y as up and x as horizontal. When on an inclined plane, that's a little bit different because, we look at it this way. Y is perpendicular to the surface, almost as if you took your inclined plane and you flipped it so it was horizontal, and x is the direction of motion. Okay? In this case, so this black here refers to sort of whatever it is, the hill or the slide or whatever it is where I have something sliding down. The red is a dot to represent my object, in which we'll draw a free body diagram, and obviously the theta is just the angle of the incline. So if I was looking at this red object, which could be a person sliding down a hill or a pug sliding down a slide, it could be anything, and we wanted to know or draw a free body diagram, and keeping in mind this idea of the coordinate system. We're not thinking up and down and left and right, we're thinking on an angle. So when I do that, one thing, my normal force is always perpendicular to the surface. There's my normal force. Really, assuming in this case, there's no friction, anything like that, the only other thing acting on my object is gravity. Gravity's pulling it down. Friction doesn't necessarily affect anything. Friction is just a factor of normal force. Anyway, so there's my gravity, and there's my normal force, and I did draw those, but I didn't draw them on the right scale. Normal force is actually smaller than gravity force. And if you think about it for a moment, you think of normal force as being the pressure between surfaces. You can imagine if something's on an angle, if you just think about the amount of pressure between that object and whatever it is it's resting on, it's going to be less on an angle than it is if you're sitting flat. Right? And that's really why you slide. So if I was going to draw this more accurately, my gravity vector would be bigger than my normal vector. And so if I look at my positive y direction, and I was trying to find the x and y components of gravity, okay, so I'm going to find F, G, X, F, G, Y. So I'm going to draw my gravity, draw a triangle here. There would be my y component of gravity. And there would be my x component of gravity. Where, this is, since this is x, this has got to be x, and since y is in this direction, it's y, and so y has to point down and away. And if you look at it then, you can kind of see, without anything else there, the normal force has got to be equal and opposite to FGY. Because it's not going up or down with reference to the plane, it's not moving, whatever this object is, my pug or whoever, he's not moving up and away from the plane, he's not moving down into the plane, he's just sitting there, and if any direction he's moving, it's only in the x direction. So therefore, Fn must be equal to FGY, the y component of gravity. And so to figure out what the y component of gravity is, and probably in a minute you're going to figure out that it's mg cos theta, and that's true, I'll just tell you why. If I was going to look at a right angle triangle, and the right angle triangle I'm going to look at is this. This must be theta, or sorry, that must be 90 degrees, and this must be then, 90 degrees minus my angle. If you think of a 180 on the inside, that angle there must be 90 minus theta. That means, considering the fact that that's a right angle as well, this right here is theta. Okay? And if that's theta, that means that FGY must be equal to FG, which is like the hypotenuse in this case, because this is a right angle, FG times cos, because it's adjacent to the angle. So FGY equals FG cos theta, therefore Fn equals FG cos theta, and Fn then. Okay, so that is the answer to the question. Why is the normal force equal to mg cos theta? That's why. It'd be nice if you could, on your test, include that drawing on your test to represent or show me how you know that Fn equals mg cos theta. Okay? I want to go one step further, which is another important thing with inclined planes is, what causes or what force is causing this object, my little red dot here, to move down the slide or down the ski hill or whatever it is it's moving down. What force is causing it to move down? The red dot to move down. And if you guessed gravity, you're absolutely correct, except for it's not purely the gravity force. Right? It can't be just gravity because it's not going to go as fast as if it was in free fall. But what it is a component of gravity. And the component of gravity, of course, is the component of the direction of motion. And in the x direction of motion, it's FGX. So the answer is the component of gravity and more importantly than just a component, it's the x component. And if you were to analyze that triangle, you would see that the x component of gravity is going to be Fg. Fg, it's opposite the angles of Fg sine theta, or mg sine theta. So whenever you're dealing with an inclined plane problem, the force pulling it down the inclined plane is mg sine theta.